Hi, I'm Jordan.
And my name is Marlon. And today we'll be presenting our final project where we created a method to determine finger and fret positions for monophonic melodies on a guitar. We use Python as our primary programming language, and we use Music 21 to help with the musical notations. To give you a little bit more background on we chose this issue and why exactly is it a problem, let's look at a guitar fretboard. Guitars typically have 6 strings and at least 12 frets. This means there are several different ways to play the same note on a guitar. Knowing this and extrapolating this to the rest of the notes on a guitar fretboard, you can see that the number of ways to play the same melody can be almost exponential. Typically, if you're an experienced guitarist, you're well aware of like the fretboard and the different notes you're able to reach with your fingers. Efficient finger and fret positions are essential for guitar players, whether you're new or you're experienced. Now let's consider a way to play a C major scale. This is one way to play a C major scale on a guitar fretboard. And as you can see, it jumps all over the fretboard. And what we're trying to achieve with our algorithm and program is a more accessible way of playing this melody. This is what typically you'll see guitarists play if they're asked to play a C scale. It's all within 4 frets, and you don't really have to move your fingers or hand positions too much to achieve this.
So we're going to be defining a fretboard class, which is what we use to represent a fretboard. The fretboard class has components of frets, strings, and tuning. So first of all, we have the fret class. We use fret as equal to 0, meaning open string, and the usual 1 through 2, 3, 4. And then class string, which is used for the strings on a fretboard, which we use 0 indexing. And the class fretboard itself, we have self-defined tuning and frets. So like we need to put those as they're going to be initialized with them. And you just casual E2, A2, D3 tuning. And we just store these as its properties. So continuing on from the fretboard class, we have its methods. And some like important methods we are going to summarize here is we have the get to the fretboard, which is so given a fretboard, you have this 2D list. Another method we have is get positions, which given a pitch note, it would return all the positions. So given this fretboard, suppose we are given A3 as a pitch note, which then returns 2, 3, 3, 7, and 4, 12. Next class method is get easiest start. And in pitches, returns the string number and the fret number, the closest starting position for the open strings. So given this fretboard, suppose we're asking for A3 and E4 now. We return 2, 3 because this 2, 3 is the closest to the open strings.
So now we'll be talking about our second class that we use to complete our project, which is called the fret position class. This represents a fret position on the guitar. So not only does it represent a fret, but it also contains information as to the string position that we're currently on, as well as fret position, and also has a reference to the fretboard that it comes from. Again, we store all the information about the notes that are available to us at this given fret position. We have defined a few helper functions and intermediary steps for our algorithm. We calculate the distance between positions, as well as Manhattan distance and fret distance. And the main crux of our algorithm is get next position, which returns the next fret position to easily play the note. To kind of give you a visualization of what exactly this looks like, let's consider a fretboard. Let's say we're in fret position 2. We want to play a new note, B3, but we want to minimize the distance between how much we have to move. If we want to play B3, we can just move down 2 frets. Now let's move on to a different method called get shortest path, which very much uses the previous method. And in a very similar way, it considers the distance from one note to another note, as well as whether it's above or below and how far apart the strings are. So let's say we're on D4 and we want to play B4. In this case, we would have to move back, and we do. And this process would continue for every note within a given melody. One thing to note is that we don't use an exhaustive search here. We chose to use a greedy algorithm because it produced good enough results for a great amount of efficiency. Without using this method, we average on times over a minute for some of our demonstrations, whereas with this method, we've cut it down to 1 or 2 seconds.
So we're going to go over a practical example. As usual, import the modules we need. So given an example melody, so we initialize the fretboard with the tuning, and now we get the easiest start. So we initialize the starting position with just where to put our fret, and then we have that fret position. And now we try to get the shortest path. And so how this works is given this fretboard, we have the C4s, the D4s there, the E4s, F4s, G4s. And what we do is we start at C again, and now we go to D, which is the next closest one. Then E is next because it's an open string. Then we continue on to F4, and then G4. A good question is, how do we know like it goes through that path? For example, why did it not start at C over there and go through this path? Something that we're going to do in our algorithm is, given this initial position, we run the algorithm, the shortest path, and to find the original initialization to be always consistent, we're going to run our shortest path the opposite way now. So we can just start at D and go to C, which gives us the shortest path backwards. And the reason why we do this is because the shortest path is at least as long as the path leading back to C. So we can just run shortest path from D to get the actual shortest path. So then this C is our shortest path initial fret position. So we're going to move on to demonstration 2. We have a score, drawing 6, which is by Walter Marsh. We're going to be analyzing 2 sections of this piece to try our algorithm. We parse this using Music 21, and we have this not really well formatted piece, but it gets notes that we need. So given the fretboard, we look at the first note and we say, okay, here's all the positions of A3. Then we see all the positions for E5, E flat 4, E4, and so on and so forth. But something we realize is there's so many positions here that just doing this by eye is almost impossible. Like, it's really hard to find the right position in chords. We're just copying it for exaggeration to show that there's so many things to consider. So let's say you ran an algorithm, we found out this output, which is where, given a note, you have the string number, and then the fret number, and the finger that's used to play it. Converting this into a tab, we have numbers where each fret number that's being used for it. We see that all the fret numbers are kind of close to each other. And so we kind of map this using a contour, which shows that there's really minimal movement in this. And it shows that our algorithm kind of confirms our initial reaction to how we get the shortest path, and it produces still good result. And then to move on to demonstration 3, we have the same score now, but we wanted to try out, okay, the guitar is actually not in this clef range, where it should be actually an octave down. We move it an octave down, and here's the Music 21 score of that. Doing the same thing, we run an algorithm, same output as in same fields, and we produce this tab. And something we realize here is that it's kind of the same thing, because instead of the leap in the beginning, we see that since E5 changed to E4, we can now play on the open strings at the 0-0, allowing for minimal movement. So we have another small contour where we have little movement.
To recap, we've created a useful method for converting a given monophonic melody into an easily playable tablature. Another thing we learned throughout this process is that there's a lot more nuances to this problem than we initially anticipated. Despite this, when comparing our output to a chromatic scale, as someone who has some experience playing guitar, this is a way I could play this scale. Granted, there are open strings where maybe playing a fifth would be acceptable, but given that it's an open string, you don't have to move your hands at all as well. Given these results, we anticipate that given an encoding melody in Music 21, our software will be able to pretty accurately predict a feasible and easily playable tablature. Some things we're considering for the future work is maybe updating our Manhattan distance, including maybe string weights. And another thing that we have to work on is an accurate finger predictor. Something that we don't consider, like how far your hand can like reach and whether your span is at 4 or can reach 1 above or 1 below. And one thing our finger predictor doesn't take into account is actual comfortability of which fingers go where. So sometimes you'll end up with fingers being crossed and not necessarily helpful for efficiency and fast movement. Another way we can expand this is chord prediction. Currently, we're working on monophonic melodies. Given how difficult and nuanced this problem is, increasing it to threefold for an entire chord might be a little more challenging. And we also want to look into improving our visualization.
Thank you very much for listening to our presentation today.